For this module, we're going to be moving from land, where we've spent most of the semester, out into the ocean. It makes sense because the geology is the study of the Earth, and the oceans cover over 70.8% of our Earth's surface. Of course, this water is all salty and has a concentration of actually 3.5% halite, which sounds pretty low, but there's a lot of salt in there, and if you've ever been to the beach, you can definitely taste it. So what we're going to do is we're actually going to look at the features along the ocean floor and along the coastlines as well. So the ocean floor covers a large area. Like I said, 70.8% of the planet. It's what we're called the blue planet. Interestingly enough, that water covers a lot of land, and so we can't really see the ocean floor at all. And that means we don't know just a whole lot about it. We're actually still learning a lot about the ocean floor. And if you look at some of the other planets that we've studied, we know more about the surface of the moon, of Mars, of Venus, of Mercury, of Jupiter at this point, hell, even of Pluto. We know more about those planets than we do our own ocean floor. And it's because, oddly enough, it's a lot easier to send a probe out to Pluto and take pictures than it is to get images of the ocean floor, just because that water's in the way. So we're going to start on the edges of the ocean and work our way down into the middle. So when we start at the edge, we're going to be looking at the margins of the oceans. And as far as ocean margins go, you really have two choices. On the left of the screen here, you see what's known as a passive margin. So a passive margin is the transition between oceanic and continental lithosphere that is not an active plate boundary. So this is something like the east coast of the United States, where there's not a plate boundary there at all. This is usually pretty easy to recognize because you have a really wide, broad continental shelf, and we're going to talk about what that is in just a little bit. But you have a really wide one here. You can also recognize it because it doesn't have a plate boundary in that case. On the other side, on this other side here, you have what's known as an active margin. An active margin is a transition between oceanic and continental lithosphere where there is a plate boundary, and that's usually a subduction zone. In this case, your continental slope is actually quite narrow, in some cases very hard to recognize. But what you do have right offshore is a trench. And a trench is the deepest part of the ocean floor. And it's created because there's a gap between the continental crust and the oceanic crust. And that leaves this big, deep gap there. The other way you can recognize an active plate margin is this accretionary prism. So what's happening here is this oceanic crust is being shoved down beneath the continental crust. But as you can see, the oceanic crust is covered in a layer of sediment. So as it's being shoved down there, that sediment's being scraped together into this kind of wedge shaped here. It's also known as accretionary wedge sometimes, of a bunch of material. Now, sometimes that's crammed in long enough or fast enough that that accretionary wedge can actually grow up above the surface, and you can actually see that happening. Something like Barbados, interestingly enough, Barbados is an accretionary wedge that's high enough that it actually peaks out over the surface of the ocean, and that's why it's an island. Well, there you go. So a passive margin has no plate boundaries. It has a wide continental slope, and you have a lot of deposition of terrigenous sediments. And that terrigenous just means it comes from land. So you have all sorts of rivers that flow towards the shore. That's where rivers are all going, right? Is basically towards the ocean. And that carries sediment from far inland. Plus you have the coast itself that erodes, and that all makes its way out onto the continental shelf. On an active plate margin, you do have a plate boundary. You can see here this subduction zone. You have a really narrow continental shelf that's just right there. And you have that accretion of accretionary prism or wedge. You also often have a volcanic arc in the area. So the sediments you have forming here are often volcanic in origin. So if you look along this map of the plates for the entire Earth, you can recognize where there is a margin that doesn't have a plate boundary, like the east coast of the United States, And you can see margins that do have a plate boundary, like the west coast of the United States. So if we look a little bit closer at those, I just want to make sure we see sort of some of these features. So this is an active margin, and this is the west coast of South America in this case. But you have your subducting lithosphere that's releasing carbon dioxide and water that makes the mantle melt. Mantle arterial rises and makes big volcanoes along the continent. And you can see your accretionary wedge forming right here, and also this trench. Now notice the trench isn't right along the coast, but it's very close to it. And so anytime you see a trench, that is a really, really good sign that you have a subduction zone. So make sure and keep an eye out for that. Now these trenches are the deepest parts of the ocean, and the deepest trench of all of them is the Marianas Trench. And the Marianas Trench is pretty interesting because it's super, super deep. The deepest part of it is the Challenger Deep, and that goes to about 36,000 feet deep. And I like this little picture because you can actually sink all of Mount Everest into the bottom of the Challenger Deep and it not even reach the surface of the water. So that tells you, we think about mountains and the land a lot, but the ocean floor actually has bigger topography than the surface does, which is interesting to think about. It's been said if you drained all the oceans, the earth would look a whole lot different because you'd actually see that topography. Now, something sort of interesting happened at the Challenger Deep not too long ago. Somebody actually went down to the bottom of it, and you may have heard of him. There he is, James Cameron. James Cameron actually dove to the bottom of the Challenger Deep in 2012. And he's the first person to ever complete a solo dive that deep. I guess if you got enough money, you can do whatever you want, right? Now, passive margins are going to look a little different. So we're going to look at some of those features. So this is like the east coast of the United States. First, you have this really nice wide continental shelf. The continental shelf is the broad, shallowly submerged fringe of a continent. So below this is all granite in this case. The widest of these are going to be occurring along the passive margin. Now, these tend to be pretty important because this is where you have oil. So the continental shelf is where we have oil reserves, and that ends up being pretty important there. And in this picture, you can see that drop off for the continental crust that's under the continental shelf. This is where you get limestone, a lot of coral reefs. There's a lot of life that lives here, which is pretty interesting. Now, because there's a big drop off, you can see the side of the continent. This is what's known as the continental slope. The continental slope marks the transition between continental crust and oceanic crust. And sometimes it's a pretty steep drop off. And what happens there is you get some pretty cool stuff. In Monterey Bay, there's actually submerged rivers under there. So the continental shelf was actually above sea level back during the Ice Age. So as sea level rises and falls, how much of the continental shelf you see changes. And this was actually all exposed. And so you had a big river creating a canyon that cut into it. And now that's submerged, the canyon's still there, which is pretty neat. You see there's these submarine canyons happen because there are landslides that come off of the continental slope. That terrigenous sediment that builds up out here on the shelf gets kind of precarious, and sometimes it rushes down. And that landslide underground is known as a turbidity current. Now, as all that moves down, it gets deposited at the bottom of the slope. We're going to look at that here in a sec too. The slope is sort of important because you have water currents that move towards the continental slope, hit it, and then rise up in what's known as upwelling. And a lot of times those are cold currents that carry lots of nutrients, which means there's a lot of fish there. When you have a lot of fish, you have a lot of birds and other stuff. And in this case, this actually ends up being pretty important in terms of marine life. So there's lots and lots of birds and whales and stuff that hang out right above the continental slope. And of course, all those turbidity currents that make their way down the continental slope, all that material gets deposited down at the very bottom where it flattens back out again. And that makes this kind of gently sloping surface here that's known as the continental rise. So this is the sloping area of the seafloor that extends from the lower part of the continental slope to the abyssal plain. It's formed by those underwater landslides known as turbidity currents. And this is your furthest extent of terrigenous sediment, which means once you go any deeper than this and any further out, most of what you get into is going to be sediment that is created in the oceans or sometimes airborne stuff that falls down. But this is sort of the outskirts of how far stuff from land can go. Once you get past that are the abyssal plains. The broad, flat parts of the ocean are known as abyssal plains. These are really deep. They're really flat. These are actually the flattest places on Earth. They didn't start out that way, and you can see the basaltic oceanic crust had a lot of topography to it. But over time, sediment buries the topography, and the sediment is when animals die and float to the bottom, you end up with piles of what's known as an ooze, which is really pretty gross to think about, right? But it's mostly microscopic critters that do that. Or it can be windblown sediment, so really fine-grained sediment that gets picked up by the wind. Or it could be dust from space or chunks of meteorites that fall out there. That is what kind of makes up the sediments out here, and all that creates really, really flat areas. The abyssal plains actually make up 75% of the sea floor, so these cover a really big area. Now, usually when we think of lush life on the ocean floor, we're thinking about the continental slopes where it's pretty shallow and the light can reach. But the sunlight doesn't reach to the bottom of the abyssal plains very much, but that doesn't mean it's devoid of life. Here is a herd of sea cucumbers that are migrating across the bottom of the abyssal plains. Gnarly looking dudes, right? Apparently these are delicacies in some parts of the world. Or even here where you can see there's been a starfish moving around. You can see the imprints from the starfish, or the holes are where there were sea worms. So there is life down here, just not as much as we see elsewhere. But one of the little bit of topography you do get out here in the deep ocean basins is seamounts. So seamounts are mainly formed by volcanic activity, and for most of the world that is thanks to volcanoes at hot spots. And you can see all these little spots out here in the Pacific. These are all basically from hot spots. And we know the Hawaiian one pretty easily. So the Hawaiian Islands are here. Here's the Hawaiian Island, the seamounts. And these are known as the Emperor seamounts as well. So those have been, that hotspot's been active for well over 65 million years. We're going to come back and look at this exact same picture here in a second. So your seamounts start along a hot spot, but as your volcanoes get pulled away from that hot spot, they sink down towards the subduction zones. And so volcanoes sink down over time. So a seamount is this, if it's underwater, and it's got a flat top thanks to erosion, this is called a guyute or goyute. What's interesting about these is you get reefs, coral reefs that form around these, but coral only grows in a really shallow ocean and really shallow water. So as the volcano sinks down further, the reefs actually grow higher and higher, but that's where you get barrier reefs or you form atolls in that case. What's interesting is this is a process that was recognized by Charles Darwin. Remember, he was a geologist first and foremost, so he noticed this process happening, although he couldn't explain why they were sinking because he didn't have that subduction to explain it. But that's pretty interesting. We can also have oceanic plateaus, which are large volcanic provinces, the largest of which is the Atong Java Plateau. So these are big areas of volcanic activity that, rather than just leaving little seamounts, leave really big, wide areas. Now, one of them is really interesting, this Shatsky Rise up here. The Shatsky Rise is actually home of the Tamu Massif. It's that guy right there. This is the largest volcano on Earth, and we've only known about it since 2013. It was actually just, we've always known it was there, the Shatsky Rise at least, but in 2013 they finally proved that it was a single shield volcano underwater. And so this thing is massive. It's on the order of about the size of New Mexico, if you look at these in complete size. So if we compare it to some other kind of famous, really big volcanoes, it's not as tall as Mauna Loa. It's not out of the water, obviously, but its footprint is much, much wider. And we can compare that to Olympus Mons. It's actually about the size of Olympus Mons, but not the height of Olympus Mons. So it's lower by a lot in volume, but it's all actually about the same size. So this is a little interesting bit on the deep ocean floor for you. When you get to the very middle of the ocean, you find the mid-ocean ridges. This is where the ocean is growing from. So the ridge, you've got volcanic activity because it's pulling apart. Volcanic activity creates basalt that fills in the hole. So you have the youngest volcano, the youngest material near the ridge, and the oldest as you move away. Now the ridges are actually really high. These are super tall, and it's because that really warm asthenosphere actually kind of makes it more buoyant, and it makes it a lot higher. And then as you go away from the ridge, everything starts to cool and contract down, and that cooler stuff and that thick mantle actually pulls it down a little bit, which is why the ridges are so high. Here's a map of the ages of the ridges. You can see in the Atlantic, right along the middle is the very youngest stuff. There's volcanoes that are still creating this here. You can see the one around Antarctica pretty easily. There's one out in the Indian Ocean. And then out here is the East Pacific Rise. And I think it's really interesting to compare the Mid-Atlantic Ridge to the East Pacific Rise. But you can see in the Atlantic, all that warm stuff is the young stuff, is really close to the ridge. Whereas in the Pacific, the really young stuff is actually spread out pretty far. And that's because the East Pacific Rise is spreading a lot faster than the Mid-Atlantic Ridge. And so that young stuff gets spread a lot quicker. So if we're looking at the ridges, we can actually see a topographic difference between these two. So a slow spreading center, one that's spreading really slowly, like the Mid-Atlantic Ridge, has an axial valley along the top. So the very top of the ridge actually has a valley. And this shows up really, really easily. We're going to make sure and look at the map in the classroom, and you can see this on the map in the classroom, even at that scale. Versus the East Pacific Rise, it is a quick spreading center, and you actually have an axial ridge. It's just really tall there. And part of that is because the slower spreading allows it to contract and cool a little bit more than the fast spreading does. And so that stands out quite a bit to be able to recognize the speed of the spreading centers that way. So if we look here on the top, you can see this valley along the top of this spreading ridge, which means it's a slow spreading. And below, you don't have that, but you do have a ridge where it's higher, and that's a fast spreading center.